Okay, Euler's method, the last little guy that we're going to work on here in section one, and it's basically using what's called local linearity, and you're going to look at a specific point or specific area and on your graph, and you're going to look at what's going on really close to that specific value of x. Okay, and so Euler's method is similar to a slope field in that it takes any curve that you're looking at and stretches your curve into some sort of linear shape. The closer you are to a specific point, the easier it is to get that linear shape. So what we're going to do is we're going to let dy dx be equal to x plus y. We're going to let f of 2 equal 0, and we're going to use the increments delta x equal 0.2 to approximate f of 3. Okay. And this is going to give us a particular solution to a differential equation, okay? Remember, this is a differential equation because it's got a derivative in it. And we're going to look for an approximation, a really good approximation to what happens at our function when f is 3. Okay, so here we go. X and y. Well, anytime we're given this information, we're given x and y, so x is 2. And y is 0. So then just follow this rule right here. dy dx is x plus y. Okay? Delta x, they already told us, is 0.2. Delta y is dy dx times delta x. So 2 times 0.2 is 0.4. And then you add delta x and the delta y. So delta x was 0.2, so that's going to give me a new coordinate now of 2.2 and a y coordinate of 0.4. So all I did was I took my x coordinate of 2 plus 0.2 and my y coordinate of 0 plus 0.4. And we're going to fill the chart in this way. And we're going to get to a really good approximation of what's going on when x is 3. So my new xy is 2.2 and 0.4. And so I add them together. That's going to be 2.6. I multiply by delta x, which is 0.2. So if you'll just humor me, I like to double check myself on this, because if you get off early on, then you'll be off the rest of the time. So I get this guy to be 0.52. So when you add, you're going to do 2.2 plus 0.2, that's going to be 2.4. And then you're going to do 0.4 plus 0.52, which is 0.92. Okay? And now I've got a new y value. Remember, we're going for that particular solution, a specific point. So now I've got 2.4 and 0.92. And I add those up. And that's going to be 3.32. And I add them up because that's what it's telling me to do with x and y. If it says x times y, then you would multiply them. If it said 2x plus 3y, then you would do that. So whatever this rule is what you do with your x and y coordinates. I'm going to take that 3.32 times 0.2, which is going to be 0.664. And then add all these up. So my 2.4 now becomes 2.6. And my 0.664 plus 0.92 becomes 1.584. And that's my new starter. So 2.6 and 1.584. I'm going to add those together. I'm going to multiply by 0.2, which is 0.8368. And then I'm going to add all that stuff together. So 2.8. Now we're getting really close because remember we want f of 3. So 2.8 and 1.584 plus 0.8368. So this is going to be 2.42. All right. And then come back over here, and this should be the last row. So 2.8. Oh, 2.8 and 2.4208. Add those together. .2208. And please double check me as I go. I can sometimes get off track on this chart. This can be a bit tricky. So 1.04416. I'm going to carry through all the decimal places because I want to be as accurate as possible. So here we go. 2.8 plus 0.2 is going to be 3. And the y coordinate, which is what we're really interested in, is going to be this 1.04416 plus 2.4208. And 46496. Okay. So the answer to this question then, this is what we're really interested in. This is what we really want to know, is going to be 3.4649. As long as I didn't make an error somewhere in all of my adding and subtracting. But Euler's method is not super hard, and it lets us look at what's going on at a pretty narrow part of the x-axis. And it's just a pattern-based formula. So you just do exactly what the top of each column says, and you should be good to go without any problems.